Hello everyone, thank you for coming to the presentation. Today we have Maxim Millen from University of Canterbury. He is a postdoctoral researcher there, and he will be talking about his own library. I think it's called O3seespy, for soil structure interaction. And thank you, Maxim, for your time, and it's all yours. Go for it.
Thanks, Pavan. So I'll start sharing my screen.
Perfect.
Oh, okay. That's not the view that I wanted, but oh dear. Oh dear. All right, I'll just going to do that kind of crappy way of doing a presentation where you look at the slides in Keynote, because it's showing the that sort of weird presenter view. So you can see the slides. Right. Okay. Yeah, this is just to remind me what I'm going to talk about, but it's essentially an overview of this package O3 or O3seespy, which is kind of a wrapper around OpenSees, makes things object-oriented and Python friendly. And then I'll talk about my research setup, which is just kind of an interest thing for people that are doing research and engineering using Python. I'm going to look at some soil structure interaction examples, and then also a little bit about debugging with O3seespy. So yeah, it's the O3 is for the object-oriented OpenSees. And I wanted, kind of to really emphasize that this library is actually just auto-built off the documentation and source code of OpenSees. So there's not a whole lot. I mean, it's whenever things get written into the documentation, it gets stripped out and put into this library. And so, yeah, full credit to the people who are contributing to OpenSees and to the documentation of O3seespy. So, yeah, I just wanted to look at the differences between O3 and then OpenSeespy and TCL, as well as the extended behavior that has been added to O3seespy, and using the MP version of OpenSees in O3, and then some debugging tips. Actually, we'll change to this other view. It should work. Oh god, better. There we go. So in O3seespy, you have it's fully namespaced. So instead of writing, so you write the O3, which is the package name, and then you access the different parts of the package in modules. So you have the uniaxial material, and then the steel O1 is an object. If I look at the same behavior in OpenSeespy, you have just the underlying package, and then each you access the OpenSees like C++ code through functions which initialize objects in C++, and you need to pass in a string to determine what object you want to create in C++. That same behavior is also in the TCL version. So these two are largely similar, and whereas OpenSees is trying to make things object-oriented and also Python compatible. So we'll look at some of those differences. The first is that you don't need to use tag numbers. So in TCL and OpenSeespy, you define tag numbers for nearly everything, and you need to kind of track which tags go to which. In OpenSeespy, when you initialize an object, it gives it a tag number, which is kind of hidden under the hood, and then you can pass that object into other objects, and it will determine what tags it should be attached to in the underlying library. So yeah, kind of I often, when I was using the TCL version, it was a lot of overhead just to track the different tag numbers. So it was a kind of an effort to get rid of them when they're not needed. The other big difference here is that we're using keyword arguments instead of this pre-arg sort of format where you needed to pass in like a string indicator before you passed in another Python variable. And so instead, you can pass in these arguments in any order, and you're using the standard sort of Python args and quargs sort of approach to define those objects. So I think, I mean, it's just kind of makes it, yeah, more Pythonic, I think is the word. Yeah, we talked about already namespaced objects, but this this really means that you type the package and then you can type in what module you're going to access, and then you can select which, say in this case, which material you're going to generate, and this really avoids, I guess, mainly spelling mistakes, which is kind of not a, I mean, it's a reasonably common bug in other OpenSees code. And also because it's now fully namespaced, if you have an interpreter, I mean, a interface, so I'm using PyCharm, it will provide all of a list of all the different arguments that you can define when you initialize the object. So it's it makes it easier to learn or to use new objects, and you can, because you kind of get that documentation. And then it's easier to read. So because when you define the steel material, you would need to know that this argument corresponds to the yield strength. Here you can actually define it using a keyword argument, so it's much easier to read. So yeah, that's kind of just covering some of the differences, but then also because of this object-oriented nature, you can then start adding behavior-based queries. So if I've just defined a soil material, often soil materials will have like a linear phase and then a non-linear phase. So when you initialize your model, you might solve it initially linearly to get the initial stress state, and then you switch to the non-linear soil behavior. Only some materials have that functionality, and so you can, in your Python code, you can ask whether the soil material object has the attribute update to nonlinear, and then if it does, then update it to nonlinear. So this is like a clean way to kind of apply that behavior in your code. The same as that if it has an option, so this is the same as, I can't remember what the underlying C++ code is, but when you want to update the Python ratio, then you can check if it has the option to set the Python ratio, and then you can update it. So, and there was kind of an effort to standardize that some material objects used, you needed to call update first call, and others were update to nonlinear, and so there was kind of an effort to make the command standard, so that you could switch out different soil objects and it would all work. The same as for all the structural elements as well, materials. This feature is just that you can, you often want to do apply a recording, and you can, you record it to a text file, but then you want to maybe plot that information straight away. And so instead you can actually just record it into a numpy array. It's a kind of a little bit of a cheat because it uses a temporary file, but it makes it very clean. For doing small examples, you can just record straight to numpy arrays using this extended recorder. Just to give you a heads up, some of the, I'll try and, after this little overview of the O3seespy, I'll then look at a couple of examples where I'll try and highlight some of these features in the code. Again, this is just extending the features so we can you might want to fix, particularly in, again, a soil finite element problem, where you would want to fix a whole lot of, like all of the left-hand side of the mesh. You can, or set equal degrees of freedom across both ends of the mesh, or in a structural problem where you might want to fix all of the base nodes, you can just apply, pass a numpy array of nodes in, and it will try to fix, apply the fixities that you want. And then you can also put a kind of catch flag. So if it's, if there is no node at that point, then either raise an error or don't raise an error. So it's quite useful for when you're using multi-processing, the OpenSees MP version. You can also generate a node mesh based on some coordinates. So this is just spits out generates a whole lot of nodes based on some coordinates. Yeah. Then also in the OpenSeespy version, there's no Winkler spring, or the spring bed model was coded in raw TCL, so there's no kind of equivalent in OpenSeespy. So in this O3seespy, we've just added this generic sort of spring bed generator to allow you to make spring bed models, which we will use in the example. There's just a little note on supporting OpenSeespy, so you can just set this is the same as when you do the initialization of OpenSees, where you define the number of dimensions and the degrees of freedom. And then you can also set this MP, whether it's true or false, will determine whether you're going to use the OpenSees MP version. And you also have the state parameter, which is useful for debugging, but usually you either have it at 0, or if you want to debug, you have it at 3. But when you have an OpenSees MP model, then you need, unless you're doing an embarrassingly parallel problem, you need to have shared nodes. So you're going to share a few nodes amongst different processes, and then they'll solve independently but have those two nodes, the shared nodes, the same. And so in that case, you kind of have to use tags to make sure that the nodes are considered the same. So you can actually provide the exact tags to nodes if you want, by just passing in the tag flag. And then also just one of the things that kind of frustrated me around was like using like the TCL version, was that you didn't have this kind of like try and fail option. Python's like perfect for that. So you can kind of, you can either apply them, if you have the mumps package available, you can apply it. Otherwise, you can apply like the profile SPD. So this is just an extended function, and you can apply the RCM numbering. And if you're using the MP version, it'll apply the RCM MP version or the parallel version. So these kind of just little extra functions that make your code a little bit cleaner, because they're kind of problems that are solved in every script otherwise. So some of the advantages of using an object-oriented version in Python is that you can now, well, my lights just turned off in this meeting room. Yeah, is that when you put on the debugger, then you can like access I've just put a debug stop point here, and then I'm going to look at the bilinear material in the debugger, and I can see all the parameters that were defined. So here I can see that E0 was set to 39.478, which is just useful to check that what you were thinking you were going to initialize, then you can check that the object did actually receive the correct number. The other one is to just print all of the parameters. So in this case, I've defined a elastic uniaxial material. I don't know exactly what parameters I've given to it in the code by just looking at it here, but I can put in a print statement to just print the parameters of that object after it's been initialized. And then the third quite useful tool is that you can actually export your O3sees code into either OpenSees Pi code or into TCL file. So that's also just kind of like you can check that what was run is exactly what you thought was run, and that's because under the hood O3 is running in OpenSees Pi. The also, so Python's main strength is its third-party packages. So you can write these additional packages, put them on PyPy, and then make them available to people, and they can install them, and they can kind of interface with OpenSees or with O3seespy. And so one of the packages that I've been building is this one called O3soil. And here we can just provide a soil profile object, which I'll talk about soon, and an earthquake signal, and it will run a site response analysis and then spit out the outputs. And so that would be the only code. If you were to, like, the script would only have to be essentially this long, and you would run a site response analysis if you just install that package. And so there's some extension libraries that are being developed. Another extension library is this O3 plot. So it's just a post-processing, and it does pre-processing as well in terms of model visualization. It is actually based on the PyQt graph library. So it's much more performant compared to matplotlib. So I'll do a little demo of that as well. But this is just looking at a soil column and a pushover analysis, and yeah, you can kind of replay your results and the likes. There's several examples for how to use O3seespy. Like the commands are all the same as as in your normal OpenSees, but it's always nice to have a few examples. So there's some examples on GitHub to just demonstrate how to use the package. And yeah, this is, I don't know why I've got this slide in. It's just an example of applying O3seespy in a Jupyter notebook, and I guess it makes it nice and readable. So. You can install O3seespy just using standard pip install O3seespy, and it'll pull it from PyPy. And then there's also full documentation, which can be found at o3seespy.readthedocs.io. And inside the docs, it has this. It has a little for each of the objects. So this is the displacement beam column. Which and it will have an example of how to initialize that that object if you want to use it. So very simple examples, but it's useful for learning a new object. And the also what I think this has code coverage. Yeah, so the code coverage. So O3seespy has well, I wouldn't say extensive, but quite a large number of tests around both initializing objects and running some like end-to-end tests. The idea is to kind of make sure that code doesn't change, and to maintain backwards compatibility, and just kind of bring some confidence that that what you run in one version will be the same as the next. And yeah, so there's an effort to kind of put a lot of, they're called unit tests for those not familiar with programming, where you just test a small amount of code each time and make sure that what you put in and get out is what you expect. So I think that's, this was just to kind of look at that we have OpenSees and C++. Then you have the compiled versions of TCL and OpenSeespy. You can also compile it yourself. And then O3seespy can handle either the pre-compiled one or the custom compiled version. and it also uses the NumPy package inside of O3seespy. And then there's some other packages kind of in the space, at least that I work in. This is that O3soil package, which is kind of an extension to run site response analysis and some foundation and liquefaction examples, problems. And there's also some designs and foundation analysis tools available in the Python packaging world. Now, what I wanted to jump to next was just kind of do a little bit of a live demo of how I set up my research, and then we'll look at a soil structure interaction example. So fingers crossed that the live demo will work. And to add to that, I actually make it live on GitHub. So I'll push commits as I go through, and it'll hopefully not be an absolute disaster. Now, if I just work out exactly where the clone button is again, must be this one. So I'm in PyCharm here, and I will just clone this repository. And so I've just, gone to GitHub, created a new repository, and then I'm going to clone it down onto my local computer. And this is, I always like to work with a GitHub repository because you can kind of track the changes that you make in between kind of stages or commits that you do. Now, one thing that is quite useful when you're doing like lots of different small research projects is to set up a virtual environment. So that kind of will just mean that that you've got your base version of Python that's installed on your computer, but then you have all these third-party packages which change version all the time. So even OpenSees, it's changing version probably about every month or something. You might do some research 1 year, and then you're going to do some other research next year, which you might want to use some updated features of OpenSees, and you want to keep, but you still want to make sure that your research from last year is still working. So you create this virtual environment which will install all the third-party packages into your virtual environment, so that they can actually be. And then you have another virtual environment for each of your different research projects, and they can have different third-party packages in them. So that's just what I'm doing at the moment. It actually has another advantage of running slightly quicker than if you were to run directly from the Python library, because you kind of made the search space a little bit smaller. Anyway, so we just initialized a virtual environment. Now, another thing that I like to do, and with the other people that I do research with, and I can't encourage all my students to have exactly the same research setup. It's useful, particularly for me, so that I can go and look at their research, and I'll know how to navigate through all their files. So to kind of make sure that that happens, is that I use this package called PyPaper, and which, full disclaimer, is something that I've just put together, but I've put it on PyPy, and it just is kind of just used to create the folder structure. So then we can, so you just kind of have these couple of commands that you put through. I think it's in that project. That doesn't look good. Okay, so that command, or running that module, has just created which is not going to show up yet. It's just created this manage.py file, which, oh, there we go, it's turned up now. This is based on the framework, the Django web development framework. So if you're familiar with that, you'll find all of this fairly intuitive. And so we're just going to run one other command, which is to create a folder structure, which was just this Python manage.py, and then I've just put a couple of initials. Now you don't need to remember those commands because I've put together this blog, which kind of explains all the GitHub stuff using PyCharm, creating a repository, and then down here you've got also the commands, the pip install, pypaper, and then these two other commands. But the same as what I've just run in my terminal here. And what that did was just create this structure where we have a folder called data, something called paper, which will store figures and also any manuscript, and then some scripts which are used to perform the research. And so what I'll do is just go and add all of those to the repository and commit them, and I'll just call that out first. Commit. Oh, didn't push. That's gotta do that. Okay, so for those of you who want to follow live, then you should be able to go to this repository. It's a public repository, and see those files now. You can be pulling it down if you want. So the what was that? I better just install some packages first so we don't have to wait. And I think I need to pin this in there as well. Okay. So what we're going to look at now that we've set up our research environment is, well, we're going to try and do some research, and that is what we're going to solve a simple soil structure problem. And I'll just give you a little brief background on my research so that you understand perhaps where this is coming from. So essentially I'm working on this project to evaluate techniques for evaluating seismic soil structure interaction in New Zealand practice. And the main summary is that we have this, particularly we're focusing on frame structures where we have a building and then we have some sort of unknown, well, poorly defined soil domain, and we have these different techniques that we can use to assess the building and account for the soil. Of course, the rigid base model is not going to really account for the soil, but it's used here as a benchmark. And then we have some single spring models that you can put under each footing. You can solve the problem with a soil finite element mesh, a Winkler foundation model, and then also this displacement-based assessment approach. And so, yeah, essentially providing guidance on how to apply each of these methods, when you can apply them, what kind of errors you will get, or limitations with those approaches. So, so that's kind of, I won't be going into that in too much detail, but instead what we're going to look at is we're just going to solve this problem, which is kind of based on a bridge pair where we have kind of a large heavy mass on a column with the foundation slightly embedded into the ground, and some essentially, how you'd call it, slightly over consolidated clay, I guess. And it's got it's just 12 meters deep, the soil profile, onto maybe some bedrock. So we want to solve this problem, and we're going to apply the Winkler beam approach. And then I also I had some, I guess, ambitious goals for this presentation, where I was also going to solve the same problem with finite element modeling, but I haven't quite I ended up we'll just look at a different finite element model because they don't just happen straight away. It's a little bit of a cobbled together effort, but we'll have a look at it. We'll do it live. What else? Yeah, so we're going to look at this particular problem, and so to do that, we have these properties which are I've just defined in this diagram. And the first thing that we're going to do is we're going to build a little database file to store that. And oh, that's not the right repository anyway. And so if I can get the right one. Now, what I'll do is that, this one is a simple one. I didn't want to just type out stuff in front of you, but essentially what you can see here is this file called gen-pier ECP. It's going to generate a JSON file which stores all of this information, but it's going to store them as objects, so kind of a structured data where we're going to define a soil object, some unit weight, and friction angle, cohesion, shear modulus, Poisson ratio. We're also going to define a soil profile and add that soil layer to the profile, and then define the properties of this foundation and this building, which we're just going to say is a single degree of freedom structure. And so when I run that command, which I can almost do, we're also going to save that file to the data folder. And this is a kind of a good trick. If you're collaborating with others in Python, then you can create a Python file at the base of your project called all paths, which will just store some of the common paths. So a path to your data folder, and then a path to the folder you have figures, where you'll save figures to, and then also if you have like external databases, you can also have them on, like I work on multiple computers where databases are in different locations. So you can use this setup to work across multiple computers or with multiple different people. It's useful for that. Anyway, we're just going to solve it, run this file and save it directly into the repository, and that will hopefully happen as, I don't know what happened there, that didn't even run. If you're, for those PyCharm users out there, you want to make sure that allow parallel run button is ticked, because it's super annoying otherwise. So just, okay, so we've ran that script, I think, twice in the end, and it's created this file, the pair, with all the pair properties. So that JSON file is just storing all the properties of our pair problem. And I will do a commit now, so that it's useful to commit this data file in case we were to change some properties, then it would highlight that we've changed some properties. So added, yeah. Now we're going to solve this problem with the Winkler beam model, and in this case, I will, yeah, I'll actually put it in here. So we'll go new Yeah. Beam on Winkler Foundation pushover. And I just wrote that code really quickly. I'd prepared this before, and I've also copied. So this Winkler beam model is based on a model that we've been developing that will based on this NZSE paper, which was essentially developing a Winkler beam model for analyzing frame structures. So so then we've taken that all of that development and put it into a Python function called set the beam on nonlinear Winkler foundation in 2 dimensions based on the paper from 2021. So now just to walk through some of the small aspects in this. The first thing that we want to do is load the this file, and so we can use the SSI models package, which loads and saves soil and structural objects and keeps their structure and keeps all the links between them. And so if I just run that debug, run this code, it's just loading this pier file, and for some reason this is running exceptionally slow. It's great for a live demo. All right, yeah, I'm not sure why that is taking so slow, so I'll just, in the interest of time, keep moving. So what, yeah, we essentially take the building, the soil, and we pass it into a function that I've written called get the moment from the rotation for a beam on Winkler foundation model. And this is just a function which is using now the O3seespy library. So this is kind of an example of its use, where we initialize an open, oh, now the debugger has finally started to work, but we'll ignore that for now. Now, so we've initialized an OpenSees instance, and then we're going to create some nodes. And so this is the syntax for creating, say, the top node, which is we need to pass in, so this little change in syntax is that you need to pass in the OpenSees instance into each of the objects. So we have creating a node which has an X coordinate. We could go X and Y. And then we've got 4 different nodes. So we have a node at the top of the structure where the big mass is. We have one at the bottom of the structure, and then we have one at the bottom of the foundation and at the kind of soil level. And we're just going to fix the soil one. And then we're going to put our masses in and define the column element, the foundation element. And then this is this function which will establish a Winkler foundation model based on this paper. So you pass in the soil and the foundation, and as well as a couple of the nodes, and define what is the orientation of the foundation axis. And that will establish a Winkler foundation model at the bottom of your foundation. And then essentially here we're just applying the vertical loads, and then we're going to push the foundation over to work out its moment rotation behavior. And with a little bit of luck, that should run reasonably quickly. And so we can see that this, oh, sorry, no axes on there, rotation and moment, and then this is the approximate moment capacity that you should expect for that given factor of safety. And you can see the model is kind of giving a nice behavior. Now, the other thing that I wanted to look at was, yeah, so, I mean, I didn't prepare the dynamic version of that example, so we're just gonna, I'll just point out a couple more things in this example, and then we can jump to the other. Just when I ran the debugger, you can just have a look to see that the building is in fact the same soil single degree of freedom building, and it has a foundation attached to it, and it has the same mass that we have specified from the example. And so this is kind of part of that data-driven development of models, where you might specify, you might create multiple different JSON files with different pair designs, and then you can just apply this sort of logic to load in your different options and evaluate them. And then the entire model is developed based on these two objects, so a building object and a soil object, and it will it'll determine the moment rotation behavior from that. Now, I did say I was trying to run a finite element version of this. It's a bit tricky because I was running it in 2D, and the problem that I've defined is a 3D problem, so you can't have an exact comparison. But essentially, this is this is just using. So we've also defined the we define a finite element mesh, and then this is a two-dimensional system which has soil and a building associated with it, and the same building and soil essentially. And then we're just developing our mesh based on, so this is that command from the in the slides where we're going to build a regular node mesh based on some X and Y coordinates. And then we're going to fix the boundaries of our mesh, and then use this quad element based on some nodes from that mesh to develop the soil mesh. Run another function to generate the foundation elements along the foundation, and then apply the pair to that model. And it kind of spits out, because it's a little bit of a rush job, it bounces around way too much. But what we can hopefully look at is the O3. This is using that O3 plot library, and we can just run through the analysis and look at the analysis, and you can zoom in, so it's very performant in terms of zooming. And this is just showing you the highest and lowest element values throughout the analysis for, you can change the properties to look at the horizontal stresses, or in this case, the maximum shear stress, and jump through. And this is quite useful if you're for debugging, because you can kind of zoom right in and check that, that in fact these nodes are, well, you can't really see it so well, but I'll pause this because it's just bouncing around too much. Yeah, that there's whether these nodes are in fact connected. So you can see that this node and this one is actually over here, and that's because of the interface that I've used. So it's useful for debugging, because I mean, being able to zoom in to that extent is like if you use Matplotlib, your computer would probably crash. So this is, yeah, just a nice performant library for that. And that is all on PyPy as well, so you can pip install that library. And then, yeah, so I was going to do a comparison between those models and run it dynamically, but you know how things are, they take way longer to develop than you hope. And the final thing that I wanted to, yeah, was to quickly show you that this library also works in for, say, a frame structure. So in this case, this is the frame that from the paper that I was, the NZSE paper, but I'm just looking at the fixed base version of that model. And again, we can, it's just going to do a pushover analysis, and you can, I mean, this is pretty boring because it's a very simple frame structure. It just demonstrates that you can kind of watch your model. And yeah, useful for debug. And so that's the last thing that I wanted to, no, we did the debugging option already, so you can, yeah, was essentially that if you were to run this pushover analysis, you can just put your debug point in and look at what you've defined. So we might, well, yeah, it's trivial to essentially you run it and then you can look at the different properties. But I'll stop at a different place. Yeah, I'm not going to go into that. Essentially, that's all that I wanted to cover, I think, in the talk. I'll just check because I made a little note at the start. Yeah, so that's kind of a cobbled together run through of O3seespy, some tips on doing research in Python, and some soil structure interaction and some debugging. It's essentially what I wanted to cover. Not under a unified theme at all, but that's all right. I'll commit that last change that I made for those that want to look at the repository. And yeah, great. That's it. Thanks, Papa.
Oh, thank you for the presentation. It was really interesting to see all the stuff. Any questions from anyone? Okay, maybe I'll ask a question which I had, like maybe a basic one. So I was just curious, you have all your, for example, we have a NumPy library, right? Like we have our OpenSees Python code. I write my code in OpenSees Python, and then I can use the functions from NumPy, right? That's how it works. So for example, I'm used to OpenSees, writing the code in OpenSeespy. So for example, I want to use the recorder options from your O3seespy. Can I integrate directly like my OpenSeespy code, and then can I use the O3seespy recorder option or something like that, and then go ahead?
Yeah, absolutely. This initialization of the library will actually initialize the same OpenSees. The only time where you might get caught out is if you're using a custom, like if you've compiled your own OpenSees, called it one package, and then you've also installed OpenSeespy, and then you import both the custom version and OpenSeespy into the same script, you will actually be running two different OpenSees at that point. It might get a little bit messy, but the yeah, you can definitely use just small features of the O3sees package in amongst your OpenSeespy code.
Yeah.
And then you can also, if you go O3.ops, then actually you're using the raw OpenSeespy code. So
okay.
sometimes like there's this print A function which hasn't been wrapped in O3seespy, and I kind of want to use that in my code, and so you can just go O3.ops.print A, and it gives you the
oh, okay.
Yeah, so it's all kind of there under the hood.
Because that would make this library more, because like if we have to completely shift to O3seespy and then start only coding in that, then it's a little harder for people to appreciate that, right? Because we just have to depend on you to do the whole thing. But if you are able to use the independent functions, then it would be like really awesome. So yeah, that's really cool.
Yeah, each of the objects that you initialize, so the main difference is the tag, like no tags, I guess. But you can access the tag once you initialize, say, an element. You can just call that element .tag, and then you can pass it into your OpenSeespy commands if you want as well. So yeah, it's definitely like there's no major problems with using the two library. I mean, the one is just a wrapper of another library. So yeah.
And one more thing is like, so this was one thing which, because recorders, that would be cool. And the other thing is OpenSees MP, for example, for OpenSeespy, we don't have the parallel computing yet available, right? But like in O3seespy, we cannot use parallel computing like OpenSees MP or SP in regular version Windows, not
so unfortunately the Windows version doesn't have it yet, but the
Linux is having. So my question is, if O3sees is able to implement the OpenSees MP and stuff, so again the same question, if I have all the code in OpenSeespy, and can I use the parallel features from your O3sees and run? Is that possible?
Yeah, that would be nice. No, you need the need a compiled version of OpenSeespy, which will support MP. Yeah, so
okay.
That's, I mean, it would be nice if someone was to solve that, but I use a Mac, so I'm not going to be pouring a lot of effort into getting that version working. So
okay, I was just curious if that would have been...
it would be nice. I agree.
Cool. I mean, anyone else has any questions? Okay, one question on the chat.
That the O3 plot, it's it's definitely, you can it's essentially just reading the output of OpenSeespy. In fact, so I use that plotting library was so I've come from like Remoco and FLAC as my software domains, and now I'm kind of combining like these bigger problems. I need to use OpenSees because it supports both soil and structure very nicely. But that same O3 plot library I use for FLAC analyses, and you just like it's just nodes and elements that you need to define, and then it will start plotting. So I guess I haven't got a nice example to show you how you would apply it for OpenSeespy, but it's definitely.
So the question might be most likely is like, for example, we have the O3sees function, we have the OpenSeespy output. Do we need to condition the output in a certain format so that the O3sees library can be used?
Yeah, actually, all it takes under like that library, it takes the X and Y position of the nodes.
Okay.
And then also a file which specifies the elements, which nodes correspond to which, like the elements to nodes. Essentially the command that you run in OpenSees where you go L nodes, but you just put it all into a single file. And then you can start adding in different like element properties that change with time. So if the stresses are changing with time, then you can add these files in, and that allows then the post processor will just change them with time, and then you can also change what you're looking at with time. But it's all it's about, I don't know, 10 lines of code that you would write, and then it spins up that interface. It's not as nice as some of the other post-processing tools, but it's useful if you are kind of using a fully Python-based approach and you want to commit everything to GitHub, then you can commit your code as well, and it's it kind of keeps that versioning problem out of it.
Any other questions?
Hello.
Okay.
Thank you. I would keep asking. I was wondering, the FEM plotting function I just mentioned is that because in OpenSees PY there are two post-processing modules. The first one is get rendering, and the second one is OpenSees visual module. And I'm not sure which module you are or package you are using to show this FEM plot. If I want to use that, I need to which package or modules I need to input in the OpenSees.
Yep. So this that FEM visualization I think was running here. So we can. Oh, you don't see my screen at the moment. It's called O3 plot. It's a separate package.
Yes.
And I mean, this is kind of a design decision. Like, I mean, in my opinion, OpenSees shouldn't contain post-processing within it, but should actually be a separate third-party, like separate package that you would install at the same time, like kind of in the same script if you want to do post-processing, just to kind of keep it as light as possible. But it's nice to have a little bit of visualization tools directly in the package. So, I mean, I don't have any gripes with it, but if you want to use your own or a different one, then you're kind of, yeah, I prefer to keep things separate. So in O3seespy, there is no post-processing, but so you use a separate Python package. But yeah, it's,
is that package? If I want to use that one because I'm new, is that time consuming for me to learn that, or it's simple? Can you show a little example?
The code that was used to create that. So in this. Yeah, in this case, it's just, it has a package loader, which is going to load, like it saves and loads the correct files that you need for the package. But under the hood, this is actually just loads a file called coordinates and a file called selected nodes if you're using, you can also plot 3D models in 2D, but that's not needed here. And then the element to nodes package is the main files that you need. And then this is just some other things because I wanted to make it really fancy and plot all these different stresses. But there's only really 3 commands. I could delete all of this. This here, and fingers crossed it would still run. So you just load the files and then you pass those files into this command plot 2D results. Oh, damn it, I've rerun the whole model. That's a good excuse to not actually show whether it works or not, but no, it's really simple. It's just you pass it into this plot 2D results and it will render your finite element model. The more you want to add, like the more different like stresses and other properties you want to add, the more kind of code you need to write to start using that. But, yeah, I don't know if it's going to work. Anyway.
Okay, thank you. Yeah.
Are you planning to put this, like, I mean, just like curious to know, like for example, these plotting packages, we have post-processing packages in OpenSees website, Pi website. Maybe you can keep your package there so that people can have more access and more awareness about this.
Yeah, so what I should, lovely, it didn't work. Okay, that's why you don't do live demos that you haven't planned. If I just go and have a look at GitHub O3seespy. So on the repo, there's the plotting library, there's the OpenSees Pi, there's soil extension library, and then also this examples one. And I believe in the examples, there are some of the examples which have which has some use of this O3 plot library. So you can see based on those examples how to use that plotting library, and also how to use some of the other features as well. So yeah, it is. Yeah, I guess other than doing talks like this, you don't really get it doesn't really get too much visualization. I mean, too much publicity, and it doesn't. I mean, it doesn't need to. I guess the more people that use it, the better, because then it will improve. So the reason why I have used that or developed this library is it's it's incredibly performant. So you can put in huge models like thousands of elements, and it will run dynamically, updating colors and everything. And yeah, and you just can't get that other than with some of these other commercial packages, but certainly not with Matplotlib. So I still use Matplotlib. It's a great library, but this particular visualization of finite element models, it seems to struggle. So
okay, thank you. Yeah, thank you very much. Yeah.
Cool. Any other questions from anyone else? Okay, looks like no questions. Okay, cool then. No other questions. Okay, cool. Okay, then we will stop the session today here. Thank you, Maxim, for taking your time for answering the questions and presenting. It's really helpful. Hopefully more people will use this library and integrate it to their, or like, that would really, you have some really excellent features. Yeah, thank you.
thanks, John. Cheers.